Hi everyone, my name is Alexey and welcome to the channel. Today I want to cover a paper published by the Google DeepMind team. Let me switch gears and then have a look at the paper. Okay, the paper called Performance Prediction for Large Systems via Text-to-Text Regression. In this paper, the DeepMind team introduces a regression model that predicts floating point number directly from text. What makes this unique is their approach. They treat regression as a sequence-to-sequence problem with constraint decoding, generating numbers token by token in a scientific notation. Their paper uses the internal Google data predicting system performance metrics from textual state. But since we don't have access to that data, I'm going to implement RegressLM from scratch and apply it to a completely different domain, which is predicting car prices from text descriptions. We will build everything step by step, starting with the word tokenizers, transformer architecture, training pipeline, and then compare our simplified implementation against the official RegressLM library. And here's what's fascinating. By the end of this video, you will see how the domain-specific implementation can actually outperform the general-purpose official version by 30%. Quick disclaimer, I'm a software engineer at Google, but everything I share in this video represents my personal opinions and does not represent Google's view. Let's dive in. The dataset I'm using comes from Kaggle, published by the University of San Francisco. And the challenge here is to predict car prices from text descriptions alone. No structured features like mileage, year, or condition, just raw text. Let me switch to the Python notebook so we can have a look at the dataset. I already downloaded the dataset, and we have 27,000 cars in that. We have 3 columns, ID, description, and price, and the price range is between 2,000 and 3 million. The description of each posting is between 200 words and 800 words. And then we have a mean and a median price. So let's see how the description looks like. We have 2022 Tesla Model X long range, available in Chicago, and then the price is 64,000. Why is RegressLM perfect for this? Because it's specifically designed to predict continuous numbers directly from text, which is exactly what we need here. So now let's start building our model, and we will begin with the tokenizer. Let's have a look at the official RegressLM implementation. They use a sentence piece vocabulary, which is a subword tokenizer with the 32,000 tokens. But for our problem, we are going to build a simple word tokenizer with just 1,500 words. Why? Because the car descriptions uses a limited vocabulary. Also, we don't want dates or brands broken into subwords. So the word tokenizer is straightforward. We build a vocabulary from text. And the way we build the vocabulary, we converting the line to lowercase, we're replacing all the commas and dots by the spaces, and then we split it into words. Okay, let's have a look at the example. The example we have here is 2018 BMW X7. We have a word tokenizer instance, we call encode method on it, and we passed our text. We get back the list of tokens. The shape of the tokens is 128. When we have a look at the numbers here, we see that only 3 tokens got non-zero values. And the reason for that is because in our text we only have 3 words. So they got encoded and they exist in our vocabulary. But other tokens are zeros. And the reason why they have a 0 values is because our path token has a 0 index. When we call decode on a word tokenizer and pass the same list of tokens, we get back 2018 BMW X7, which is expected. The reason why it's all lowercase is because when we build a vocabulary, we convert all the words to the lowercase. So that's why when we call a decode, we got all the text in a lowercase. Let's move on to the number tokenizer. For the decoder, the official RegressLM uses P10 tokenization with constraint decoding, which means that it's representing numbers in scientific notation where only valid tokens are allowed at each position. So the constraint decoding is implemented with the possible next token method. It gets the index of the next token and then checks what are the possible tokens that it can generate at this position. So for example, at the position 0, where no tokens are yet generated, the only possible tokens are plus and minus. I'm following the same approach with a simplified version, where I use a fixed digit exponent format. This makes the tokenizer simpler while keeping the core idea the constraint decoding to guarantee valid outputs. Let's have a look at the implementation. Okay, so our number tokenizer has digits from 0 to 9, dot, exponent, plus, minus, pad for padding, and boss to mark at the beginning of the sequence. The core concept behind the number tokenizer is actually the possible next token. The possible next token makes sure that we return a list of valid tokens for the next position. So when the position is 0, which means that no tokens are generated yet, the possible two tokens are plus and minus. For the second position, the possible tokens are from 0 to 9, and for the next position, the only possible token is dot, and so on and so forth. Let's have a look at the example. Our test value is 27,185. So when we encode it with the number tokenizer encode, we get tokens representing in a scientific notation. And when we decode it back, we got a slightly different number. So this is because we are using 4 significant digits, so we lose accuracy during the float to text and to float conversion. And that's a trade-off for keeping the tokenizer simple. The main difference from the P10 tokenizer is vocabulary size. So they use 33 tokens and we use only 16 tokens here. So this is all the tokens that we use to tokenize the number. But the core mechanism, constraint decoding, is the same proven approach from the paper. Now let's build the encoder-decoder architecture. As we finished with tokenizers, we can have a look at the more serious stuff. We will have a look at the encoders. So the official Regress implementation uses the vanilla encoder, and it also uses the rotary position embedding. It's a more modern approach where the positional information is applied directly to the query and the key vectors during the attention computation, rather than being added to the input embeddings. Let's have a brief look at the vanilla transformer encoder layer. So this is the transformer encoder layer with the rope support. It defines the query key value and the output. It has 2 normalization layers, it has a dropout, and then it uses ReLU as the activation function. This is the self-attention block. As you can see, it passes the rotary position embedding, and as we talked a little bit earlier, it applies rotary position embedding directly during the attention computation. But for our simplified version, we'll use PyTorch transformer encoder layer directly. Same underlying architecture, just less custom code. And our simplified version uses a classical sinusoidal positional encoding from the original transformer paper. Let's have a look at our transformer encoder. So our transformer encoder architecture is straightforward. We start with an embedding layer. This is the lookup table that converts token ID into a dense vector. For example, the token ID for BMW is mapped to a 256-dimensional vector. Then we add a sinusoidal positional encoding. This tells the model at which position the word appears. But the core here is the transformer encoder layer. This is the PyTorch standard transformer encoder with the 2 layers. Each layer has a multi-head attention and a feed-forward network. We use 4 attention heads and set the feed-forward dimension to 4 times the model dimension. That's 1024. Let's now calculate the number of parameters used by our encoder, so we can deeply understand what's going on underneath. We have 4 attention heads, query key value and the projected output matrices. So each matrix has the 128 by 128 dimension plus 128 for the bias. So remember, the attention hash is just a linear transformation, so that's why we have a D model by D model, and by default we use 128 as the D model size. So that's why when we multiply that, 128 by 128 plus 128 for biases, and then we multiply it by 4, we have 66,000 parameters per layer. Then we have 2 layer normalizations. We have 2 layers per encoder. Each layer has 128 by 128 parameters, and we multiply it by 2, and we get 512 parameters per layer. So the layer normalization is basically used to have a 0 mean and 1 as the variance. It stabilizes the training and helps the model to converge faster. Then we have a feed-forward network with two linear layers. The first layer has 66,000 parameters. Is because the input is the 128 and then the output dimension is 512. So we transform from the low dimension to a high dimensional, and that's because we want our model to learn more. We give a room for our model to learn the task that we are training for. Then the second layer basically transforming it back to the original space. So from 512 to 128 and then post biases, it's again 65,000 parameters. And in total we have 131k parameters per layer. Okay, let's calculate how many parameters we have in total. So we add up the 66,000 from the attention head, then 512 from the layer normalization, and then 131,000 from the feed-forward network. We got 198,000 parameters per layer. Then we have two layers, so we multiply this number by 2. Then we have a final layer normalization from here, and then we add up two numbers. This is the number from the network itself, and this is the number we got for the embedding size. So our total number of parameters is 588,000 parameters. Okay, let's run through the example that we had before. It's a 2018 BMW X7. We use tokenizer to create tokens. Then we create a padding mask. So why do we need a padding mask? The padding mask we need to tell the model to not to spend the attention on the padding tokens. Then we got an encoded tensor, and then we calculate the total number of parameters. So the input text is 2018 is BMW X7. The text token has the 128 dimension. Padding has the same dimension. The number of non-padding tokens is 3. It is expected because all other tokens, as we saw before, has 0 values. So they would not participate in the attention. And then we have the encoded representation, which is 1 by 128 and then by 128. That's because each token here has a 128 dimension in the embedding space. Then the total number of parameters is 588,000. And it's actually the same as we calculated manually here. So far so good. This encoded representation will be fed into the decoder to generate the price predictions. Now let's build the decoder that generates the numbers. Now we arrive at the decoder, the component that is responsible to generate the price predictions. Interestingly, the decoder is much simpler compared to the encoder. So the official RegressLM implementation actually uses the PyTorch standard transform decoder layer and transform decoder directly. Our simplified implementation follows the same approach. We also use PyTorch built-in transformer decoder layer. What is more interestingly is that for the position encoding, if we go here, we will see that they use the same sinusoidal position encoding as we used in our implementation for the encoder too. Let me switch to our transformer decoder. So the key difference from the encoder is that the decoder is autoregressive. It generates outputs one token at a time, where each new token depends on all previously generated tokens. The decoder has a similar structure and a similar architecture to the encoder. The core is PyTorch transformer decoder with 2 layers. So each decoder layer has 3 main components. The first one is the mask self-attention. The decoder attends to its own previously generated tokens. The second one is that it's a cross-attention. The decoder attends to the encoder's output, and then the feed-forward network, which is the same as for the encoder. Finally, we have a linear output layer that projects from D model to our vocabulary space. So this is needed to produce logits, raw scores for each possible next token. Now let's go to the forward method. So the forward method handles both training and inference. During training, we get the target tokens, which represents the final numbers that we're teaching the models to generate. During the inference, the target tokens is none, so we call the generate method. Let's focus on the training path first. So the most critical part here is the generate square subsequent mask. This creates a causal mask, a triangular matrix that prevents the decoder from cheating by looking at the future tokens. So think about it this way. When predicting the third digit, the model should only see the first and the second digits and not the fourth and fifth. So the mask enforces this by setting future positions to negative infinity, effectively blocking attention to them. And then we go to the transformer. So the decoder then processes the embedded tokens through the transformer layers. Notice it receives two inputs, X, the target tokens, and then the memory, the encoder output, the encoded text description. This is where the cross-attention happens. The decoder uses the encoder understanding of our text that we used before, for example, 2018 BMW X7, to guide its generation of the price. And then finally, we project through the linear layer to get logits for each token in the sequence. And now let's go to the exciting part, the generate method. So the generate method is where the autoregressive generation is happening. This is how the model actually produces a price prediction during inference. So let's examine this loop here. We start with a single token beginning of the sequence, and then we enter a loop that generates one token at a time, up to 15 tokens maximum. That's enough for our scientific notation. Then at each generation step, we run a forward path through the decoder with all previously generated tokens. Then apply constraint decoding by masking invalid tokens to negative infinity. Then select using the greedy method, the highest probability for the next token, and then we continue until we get the padding token, so we break out of our loop. Now let's test it. We use the encoded representation from our 2018 BMW X7 example and generate a price. So before training, the decoder output essentially random tokens because the weights are randomly initialized. We might see some random things. So this is the predicted price right now, which is ridiculously high. But then if I run it again, you see the price is different, and then it might even predict 0. And now we have both pieces, the encoder that understands the text and the decoder that generates numbers. Let's combine them together and complete our simple RegressLM model. Our simple RegressLM is beautifully simple. It's just a wrapper that connects the encoder and the decoder together. Under the init, we have two components. The encoder has the vocabulary size of our word tokenizer, and then the D model is 256 with just two layers, and the decoder with the vocabulary size of the number tokenizer, the same dimension for the D model, and the number of layers also 2, so we keep it very simple. Now we arrive to the forward method, which is incredibly simple. The first, we pass the tokens through the encoder to get the presentation of our text description. Then, depends on the mode, it can be inference or the training. If it is training, we pass it through the decoder, we pass the encoder output and our target tokens so we can learn and predict our final prices. But if it is inference, we call the generate inside the decoder and only passing the encoder output. Okay, now let's go to the predict batch. The predict batch handles all the boilerplate code. It puts the model into the evaluation mode. It then generates the tokens, and then it puts them into the appropriate device, CPU, GPU, or Apple Silicon, and then it runs through the forward path, and then it predicts the final output. This is much more efficient than by calling the forward part in a loop, and this is because we can process the one batch at a time, which is much more efficient than a single example through the while loop. Let's run this. And then we use the same example, 2018 BMW X7, and then the predicted price is even negative. So if we run it multiple times, we will get the different numbers. Yeah, so this is because the model is untrained. Now let's have a look at how many parameters we have. So if we run this cell, we'll see that we have 4 million for the model parameters, and then it's split between the text embedding parameters, and then the encoder parameters, decoder parameters. So if we have a look at the closed loop, that we have the same number of embedding parameters as we had before, but for some reason the encoder parameters is almost 2 million, and it is 4 times larger than we calculated before. So the reason for this is because when we calculated the number of parameters for the encoder for the first time, we used a different D model size. So before we used the D model size, which is 128. but for our training we use 256. You see the model size is 2x larger, but the number of parameters is 4x larger. And why is that so? So if you remember, when we had a look at the encoder here, you see that all our parameters calculated based on the attention heads, most of them. And then to calculate how many parameters for the attention heads, we have to multiply D model by the D model. So, and before we had 128. So if we replace it with 256 and then split the 256 by 2 multiplied by 128 and then replace it with here, we will have a factor of 4 before that. So that's actually why we have our model is almost 4x larger. And now we are ready to train this model and see if it can actually learn to predict car prices. Let's set up the training loop. I wanted to finish this video in 30 minutes. Let's see if I can succeed. First, we need a PyTorch dataset. This is a standard pattern in the PyTorch. It tells the framework how to load and process the data. In the init, we store the description and prices and keep references to the text tokenizer and the number tokenizer. And the get item does the heavy lifting. It gets the description and the price from the ID. It converts the description to tokens. The same applies for the price. The price is converted to the tokens. And then the get item returns both description and the price tokens. Then let's create a training dataset. So for the training dataset, we're going to use a subset of our data. A set of 25,000 examples from our dataset. And you might ask why not all 27,000, and that's because we are holding out 2,000 for validation. We want to see how well our model generates the unseen data. And then we wraps our dataset in a data loader. So this tells the PyTorch from where to load the data, and the data loader will handle everything. It accepts several parameters. The first one is the batch size. So we're going to process 32 examples at once. Larger batch size may be more efficient but will consume more memory. And the shuffle parameter. So the shuffle parameter randomizes the order of each epoch. So this prevents the model from learning patterns based on the data ordering. Then we go to the optimizer. So as you can see, for the optimizer we use the Adam, which is much more better than the stochastic gradient descent, because the Adam adapts the learning rate for each parameter automatically. So it's better than the stochastic gradient descent. And then for the criterion, we're going to use the cross entropy loss. You might ask, why we going to use the cross entropy loss for the regression? But remember, we are not directly predicting the number, we are predicting a sequence of tokens. So each position in the sequence is the classification problem, which of the 16 tokens should come next. And then if I run this, we'll see that my device in the MPS, which is Apple Silicon, we have 25,000 training examples, which represents 782 batches. Now for the actual training. We are training for 30 epochs, and the epoch is the complete pass through the entire dataset. Let's have a look at the training loop more closely. First, we set the model to the training mode. This is just like a dropout. Then we go to the data loader and get out the first batch, which is 32 examples. We move description and price tokens to the device, which is MPS in my case. The next two lines are more interesting. This is called teacher forcing. Teacher forcing is the model the correct previous tokens and ask to predict the next one. Then we have a forward pass through the model. We got the logits, the probabilities for each token occur at each position. Then we use them to compute the loss using the cross entropy loss. And the next three lines are the standard PyTorch pattern to zero out previous gradients, compute new gradients, and then update weights using new gradients. And the final steps, we just accumulate the total loss, and then we average the loss, and then we report it for each epoch. As you can see, there was a training running, and we went from 0.75 to 0.48 after 30 epochs. Lower loss means the model is getting better at predicting the correct tokens, but loss alone doesn't tell us if the model makes good price predictions. For that, we need a validation. Because the model training is already done, let's move to the validation phase. For the validation subset, we use 1,000 examples. We put the model in the evaluation mode, and then we iterate in batches. The batch size is equal to 32. We get the batch of data. We use the predict batch, the helper function that we discussed before, and then we get the generated price predictions. We put it in the predictions, and we also put the actual price in the actual list. For our metric, we use MAE, mean absolute error. For each example, we compute absolute value between predicted and the actual price, then average across all examples. Why MAE instead of MSE? So the reason for that is clear. The MAE is interpretable. If MAE is 5,000, the model is off by 5,000 on average. MSE would give us something like 25 million, which is very hard to interpret. And now the exciting part, let's see our results. Okay, our validation MAE is 17,000. And then let's go through the examples here. So the first one has the predicted price almost 29,000, but we predicted almost 25,000. The difference is 4,000. Then the difference is 1,000. Then we have a difference of 11,000, 21, and 30,000. This is actually not bad for this small model, and we only trained for a few minutes. Okay, from these examples alone, we can see that the model clearly learned patterns. It knows recent years cost more, and certain brands like BMW or Mercedes are more expensive. Now, before we compare our results with the official RegressLM implementation, I want to ask to have a look and visualize how the model generates each token. So let's test a single example from a validation set. We got the example description and the example price. We printed before we process it. Then we got a text tokens, so we processed the example description in text, and then we used our word tokenizer to encode it. So we got our tokens. We put the model in the evaluation mode, and then we ran it, the single example, through the encoder. So we got the memory. Then we use our number tokenizer to tokenize the price. So we got the target tokens. Then we have our generated sequence. So far nothing is generated. So we have a BOS token beginning of the sequence. Then we take what was generated so far and run it through the decoder using the encoder memory as well. As output, we got the logits. So the logits are the raw scores for each possible token in our number vocabulary. So the second, we apply the constraint decoding. The model uses possible next tokens function to figure out which tokens are allowed at this position and sets all invalid tokens to negative infinity. Then we convert the mask logits to probabilities using the soft mask. This is crucial. It tells us how confident the model is about at each position. A probability of 100% means the model is absolutely certain, and a probability of 20% means it's uncertain and considering other options. Then we got the token with the highest probability by using the argmax. Then we use the token ID to concatenate with our generated sequence so far, and then the loop repeats. And the loop repeats until we got the padding token. Now let's see everything in action. Let me scroll down here. And here's our example. We have a Mercedes-Benz E-Class description, and the price prediction is 24,000. We got our target price tokens and then target price string. Then the loop is happening. Generated so far, there is nothing is generated, and then the valid tokens are plus and minus. So the model generates that plus is 100% and the minus is 0. And then so the predicted next token is plus. Then the second iteration, we predicted so far plus. So the next valid tokens are from 0 to 9, and then we have a top probabilities. We have 2, which has 72 probabilities, and then 72%, 3 is 17%, 4 6%, and so on and so forth. So the predicted next value would be 2. And then the loop repeats. So we can see that the model in action, we see that how it predicts probability for each token to occur at each position. Alright, we built our simplified RegressLM from scratch. We trained it, we validated it, we even visualize how it behaves. We are getting around 17,000 mean absolute error on acquire price predictions. But how does this compare to a Google DeepMind official implementation? Now we are using the official RegressLM library. We use the from scratch method and we pass the model parameters. We got similar things. The D model is 256. We have 2 encoder layers, 2 decoder layers. The max input length is 128. The maximum number of epochs is 30 and the batch size is 64. If I scroll down for the training, we're gonna use the same training subset and the validation subset as we used for our from scratch implementation. Depending on your hardware, this might take some time to run. For me, it took around 10 minutes to finish. Now let's scroll down for the validation. So we create an example input using the RegressLM standard objects. Then we use sample to get the prediction. We convert it to float and then we append to the official predictions. And then we calculate the official MAE. Let's see what we have here. We have our simple RegressLM MAE, which is 17,000, and then an official RegressLM MAE with 25,000. When we run through the sample predictions, again, only 5 examples, we get a small table, the actual prices predicted, and the error. We see that the difference is about 7,000 MAE, which is 30% improvement compared to the official RegressLM implementation. So what we see here? We see that our simplified implementation actually outperformed the official version by 30%. This is unexpected, but it's very good. But I want to make it very clear. This isn't because we are smarter. We tuned the model for specific task. They probably optimized for the general performance across many tasks, and the core insight of RegressLM, treating regression as a sequence-to-sequence with constrained decoding, works brilliantly even in simplified form. But for now, I want to say thank you, and if you enjoyed this video, let me know what paper to implement next, and if you build something cool, I would love to know about it. Thanks for watching and have a nice day.